Hey everyone, so in this video we're going to be continuing our series of videos on confidence intervals. So just a review of confidence intervals for means when sigma is known. Remember we had this formula here where we took the sample mean and we added and subtracted this margin of error, which was made up of z alpha half, which is our critical value, and then sigma over the square root of n, which was our standard error. And then we came up with two numbers out of this, and that was what made up our confidence interval for mu, the population mean. The only problem here is that sigma is not often known. It's not often that we don't know the population mean, but we do know the population standard deviation. We either know both of them or we know neither. So it's not very realistic for this formula to pop up very often. So what we need to do is come up with a formula that adjusts for us not knowing what the population standard deviation is. And this is where the t-distribution comes in. So just like the normal distribution, the t-distribution is also symmetric and unimodal, and it kind of looks like a bell, just like the normal distribution. So there's only one standard normal distribution, but there are infinitely many t-distributions. And we'll see an example of this in just a moment. So what are the differences between the two? Well, the t-distribution is going to be wider and flatter than the standard normal distribution. So that's one difference. And then the other difference is that the t-distribution only has one parameter. So the t-distribution is actually always going to be centered at 0, so we don't need the location or the mean as the parameter. But the other thing that affects what the t-distribution looks like is the spread of it. And the spread is going to be affected by what are known as degrees of freedom. And this is the one parameter of the t-distribution. We usually denote the degrees of freedom by df, or this Greek letter nu. And I'm going to use df here, just because it's a little bit more intuitive. So the way we calculate the degrees of freedom is to take the sample size n and just subtract 1. That's it. So as df increases, the t-distribution converges to the standard normal distribution. So in other words, as the sample size increases, the t-distribution is going to look more and more like the standard normal distribution, like the z-distribution. So here is what the t-distribution is going to look like. So when our sample size is lower, let's say our sample size is 2, then our degrees of freedom is going to be 1, which represents this red t-distribution right here. And as we increase our sample size, let's say we increase it to 3, then the degrees of freedom will be 2, and that's going to make the t-distribution look like this orange curve here. So as we continue to increase our sample size, this curve right here is going to approach the shape of this black curve that looks like it's at the top of everything else. And that black curve represents the standard normal curve, or the z curve. So now, how do we use the t-distribution to construct confidence intervals? So remember, we started talking about the t-distribution because we wanted a way to handle the situation for when sigma, the population standard deviation, is unknown. But as we saw from the image, it looks like the t-distribution is also really handy when we're trying to handle smaller sample sizes. So what that means is, as long as the population is normal, then we could also handle smaller sample sizes. So since sigma is unknown, what we're going to do is we're going to estimate it using S. And remember, S was the sample standard deviation. So when we put it all together, our formula for the confidence interval is actually going to look pretty similar to when we were constructing the confidence interval when we were using z, when we knew the population standard deviation. This is just going to be x bar plus or minus t alpha half, which is our new critical value here, times the standard error, which in this case, instead of sigma over the square root of n, we're going to have s over the square root of n. So just like before, this piece right here, t alpha half, is going to be our critical value. S over the square root of n is going to be the standard error, and then this whole thing is going to be our margin of error. So remember, the difference between z and t here is that there's only one z distribution. There's only one standard normal distribution. So we have that one table that tells us everything that we need to know about that one distribution. But with the t distribution, we have to be careful because now we have many t distributions. We have actually infinitely many t distributions. So when we're using this t table, we have to make sure we're using the correct t distribution. And remember, the degrees of freedom will uniquely define which t distribution we're working with. So as long as we know the degrees of freedom, we can look up any value that we need to look up in the table. And remember, the way we calculated degrees of freedom was to take the sample size and just subtract 1. So as long as we know what the sample size is, we can easily find what the degrees of freedom are. Now, the other thing we have to be careful with here is that the z-table, remember, had the critical values in the margins of the table and the probabilities or the percentiles in the body of the table. And the t-table is actually the other way around. The t-table is going to have the critical values in the body of the table, while the probabilities are going to be in the margins of the table. So remember when we were looking for, say, the 80th percentile of the standard normal distribution, we would find that in the middle of the table somewhere, and then check whatever value of z from the margins corresponded to that. Now with the t-table, it's going to be the other way around. So just like before, our rules with alpha are going to apply. So when we're dealing with a 90% confidence level, that means alpha is going to be 0.10 because 10% is what remains. So alpha half is going to be 0.05. Similarly, with 95% confidence level, that means alpha is going to be 0.05, and that means alpha half is going to be 0.025. So when we look this up on the table, we're going to find that alpha half value up here, and we're going to find our degrees of freedom here. And where those two meet is going to be our critical value in the middle of the table. So for example, when n is equal to 10, our degrees of freedom, df, will be 9. So t alpha half, if we look this up on the table, df is going to be 9, and alpha half is going to be 0.05. So when we look up where those two meet, we're going to find that it's going to be 1.8331. So that's our critical value. That's our t alpha half. And then another example here, when n is equal to 13, we're going to have df equal to 13 minus 1, which is equal to 12. And then we're looking for 95% confidence. And remember, when we're looking for 95% confidence, that means alpha is equal to 0.05. So that means alpha half is equal to 0.025. So when we look this up on the table, we're going to be looking for 12 degrees of freedom, and we're going to be looking for 0.025 for our alpha half. And when we find where those two meet, we'll find that our critical value is going to be 2.1788. So T alpha half is equal to 2.1788. So that's how we look up critical values on the t-table. So let's look at an example. So suppose we're interested in estimating the true mean height of NBA players, and we're going to assume the distribution of heights is going to be normal. So in a random sample of 16 players, the average height was 78.7 inches with a standard deviation of 3.1 inches. So what if we wanted to construct a 90% confidence interval for mu? And mu in this case is the true mean height of NBA players. So as always, I always recommend listing out any of the information that's given to you. So what we have is n equal to 16 because we had a sample of 16 players. We had x bar equal to 78.7 because that was our sample mean from our 16 players. And then our sample standard deviation S is going to be 3.1. And then we're asked to find a 90% confidence interval. So just like before, we actually have all the inputs to the formula given to us already, and really the only thing we need to go and find is T alpha half, which is our critical value. Our sample size was 16, so that means our degrees of freedom, df, will be 15. And we were looking for 90% confidence, so our alpha level is going to be 0.1. So alpha half is going to be 0.05. So when we look this up on the table, we find 15 degrees of freedom right here, and we find 0.05 here. So the critical value here is going to be 1.7531. So that's going to be our T alpha half in the formula. So that was the part we were missing. So now we have all the information we need for the formula. So when we plug this into the formula, we get 78.7 plus or minus 1.7531, which was our critical value, times 3.1, our standard deviation, over the square root of 16, our sample size. And that gives us 78.7 plus or minus 1.359. And it gives us this interval right here. And we're going to interpret this the same way we did when we were doing confidence intervals using Z. So we'll say we are 90% confident that the true mean height of NBA players is between 77.341 inches and 80.059 inches. So sometimes it might be a little bit challenging to remember whether you should use Z or whether you should use T. And this is a helpful little tree diagram that can show which one you should use in which situation. So first of all, we have to ask ourselves, are we trying to construct a confidence interval for a mean or for a proportion? And if we construct a confidence interval for a proportion, then all we need to do is check our conditions. Is NP greater than or equal to 5? And is N times 1 minus P greater than or equal to 5? If so, then we're allowed to use Z for our confidence interval. And if not, then we don't have enough information to construct the confidence interval. So looking at this side, when we're constructing a confidence interval for a mean, we're going to check, is our sample size greater than or equal to 30? If it is, and we know the population standard deviation, then we're going to use Z. If it's not, then we're going to use T. Remember, that was when we introduced the T distribution in the first place, when we don't know the standard deviation of the population. So now on this side, if our sample size is not greater than or equal to 30, then we have to check whether or not the population is normal. Because if the population isn't normal and n is less than 30, then we're not able to use the central limit theorem, and then we don't have enough information to construct the confidence interval. But if the population is normal and we know the population standard deviation, then we can use Z here. But if the population standard deviation is not known, then we have to use t. So I know this is a lot, but really what it comes down to is, do we know the population standard deviation? And if we do know the population standard deviation, then we're going to use z. And if we don't know the population standard deviation, then we're going to use t. Now, the other stuff here is just checking for normality. Is n greater than or equal to 30? Do we have a normal population? Is np greater than or equal to 5? Is n times 1 minus p greater than or equal to 5? All these are just normality checking. And if we can declare that the distribution is at least approximately normal, then all we need to do is check whether or not we know the population standard deviation. And that'll tell us whether we should use z or whether we should use t. So again, I know this is a lot, but if you have kind of like a vague image of this tree diagram in your head, it'll kind of help you get a better feel for how to navigate through certain situations depending on what information you have available to you. But anyway, that's all for this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.